Hello and welcome. This is General Popat. We are discussing stress distribution. This is the third video. In the previous two videos, we have discussed there were basic five theories to stress distribution, in which we have discussed Bose-Einstein's theory, Westergaard's theory, and Newmark's influence charts. Let us discuss other remaining two. So, we are going to discuss isobar diagram and contact pressure concept. Let us start with isobar diagram. Isobar diagram, that is a basic curve which is connecting all the points below the earth surface which are having same vertical pressure. Or in other words, we can say it is a contour of points having same vertical stress. An isobar is a spatial curve which is passing from all the points which are having vertical stresses. Generally, isobar diagram is in a shape of electric bulb and it is symmetrical to its vertical axis. Let us understand isobar diagram through this diagram. In this figure, we can see that the horizontal planes are having equal amount of vertical stresses at same radius from the axis of loading, and that points make a pressure bulb. Inside of that pressure bulb is having greater amount of vertical pressure, and outside of that pressure bulb is having lesser amount of vertical pressure. So we can conclude that isobar diagram is showing, or pressure bulb is showing, decreasing value of stress from inside to outside, because insider values are greater than outsider values. Let us take an example for understanding of isobar diagram. If sigma z is 0.20 into q, that is 20% of q. Say if we want to plot for 20% of loading the isobar diagram, so we can use sigma z is equal to ib into q by z square, as well as ib will be taken as sigma z into z square by q. We have made ib as a subject of the equation. Here, putting sigma z value as 0.2 q, we are getting ib as 0.2 into z square. So it will vary with the depth of z, with the square of depth z. So that is all for isobar diagram. Let us move to contact pressure. So contact pressure is nothing but the vertical pressure coming on the contact surface of a footing and underlying soil mass. It is sometimes it is assumed in simplified assumptions that contact pressure or pressure under a surface or under a footing is always uniform, but it is not always valid. We should understand that the contact pressure or vertical pressure will depend upon two things, that is flexural rigidity of the footing and the elastic properties of the underlying soil mass. So it will depend on these both. It is not directly assumed as uniform. Let us see one by one example of contact pressure. Let us see the first case of flexible footing made up with saturated clay. So this figure is showing that a saturated clay and a flexible footing under uniform loading. Now under uniform loading, if this footing is flexible, then settlement will be in a bowl shape like this, and its maximum point will be in center here, where if the saturated clay and the rigid footing are connected and uniformly loading is given, then as it is a rigid footing, the settlement will be uniform, and in vice versa cases it will be like minimum in the center and maximum in the peripheral items. In theory, elastic theory, we assume that the at the ends of the footings there will be a infinite pressure, but practically it is not possible, so we have to assume these pressure at the ends as maximum and at center as minimum. In case of sand with flexible footing, in this case flexible footing is there lying on the sand and under a uniform loading. So these will behave like on the edges the displacement or settlement will be maximum and in the center it will be minimum, and vice versa in the case of rigid footing on sand and under uniform loading it will behave like a bowl shaped settlement and maximum point will be in center. So this is the behavioral theory of contact pressure. Let us move to numericals now. Before solving numericals, you must understand and you must know all the formulas of this chapter which are basic to this. Let us solve problem number 1. Now, first problem, for a point load of 150 kilonewton. So there is a point load and it is value having 150 kilonewton. Find vertical stress at 2 meter depth. So depth is given of that point and along axis using Boussinesq and Westergaard theories. So we have to find out vertical stress at 2 meter depth and we have to find out it along axis of loading, and we have to apply Boussinesq and Westergaard theories. Consider Poisson's ratio as 0. Here guys, numericals of this chapter are very much simpler. If you do understand the problem clearly, there is very much simpler and easier way to solve that. Let us write down given data first. So for given data, we can take Q, that is 150 kilonewton, Z is equal to 2 meters and R is given 0. Why we took R is equal to 0? Because we are told to find out the stress at 2 meter depth along axis. So as we are going along axis, radius of the point will be by default 0. Now let us go further using Boussinesq's theorem. Now according to Boussinesq's theorem, we must remember the formula, that is sigma z is equal to 3 by 2 into q by pi into 1 by z square, and in bracket 1 upon 1 plus r by z square and whole raised to 5 by 2. So this is very basic Boussinesq equation for point load, or we can say concentrated load. Now here q is given, pi we know that, z is given, r and z both are given, so we are putting all the values, q as 150 kilonewton, z as 2 meter and r as 0. Putting r 0, it will make it as 1 and sigma z value comes out as 17.90 kilonewton per meter square. See guys, Boussinesq's theorem gives us the vertical stress value as 17.90 kilonewton per meter square. Let us find out what Westergaard's theorem gives us. Now, remembering sigma z value for Westergaard, or equation for Westergaard's theorem, that is q by pi into 1 by z square and in bracket 1 upon 1 plus 2 into r by z square and whole raised to 3 by 2. So this is Westergaard's equation. You can also use sigma z is equal to IW into q by z square, and you can put IW and IB values as well. Now putting q as 150, z as 2 and r as 0, I am getting sigma z value as 11.93 kilonewton per meter square. So you must understand that Boussinesq and Westergaard both are giving different values here. They both are used for vertical stress calculation, but both will give different values. There is assumption that Boussinesq and Westergaard both are correct in different cases. Boussinesq and Westergaard both are correct, but both are applied in different cases. When we will go in deep, we can understand where we should apply Boussinesq and where we should apply Westergaard. But up to now, you should understand both very clearly only. Let us move to second numerical. A concentrated load of 50 kilonewton is applied. So here Q is equal to 50 is given. X on a surface of soil. Plot the variation of vertical stress increment due to load on a horizontal plane at a depth of 2 meter up to horizontal distance of 3 meter on one side of center. So vertical depth is taken as 2 meter and horizontal distance up to 3 meter should be taken. So let us calculate this by writing given data first. So given data Q is equal to given as 50 kilonewton, Z is equal to given as 2 meter and R should be taken as 0, 1, 2 and 3 on one side of center. So let us remember the basic equation for this. When you are not told to find out with Westergaard, you should by default calculate with Boussinesq's equation. Now let us remind the solution equation. Sigma z is equal to 3 by 2 into q by pi into 1 by z square and in bracket 1 upon 1 plus r by z square and whole raised to 5 by 2. So by using this equation and putting q and z value as well as r is equal to 0 for first attempt. So in first attempt I am putting r as 0 and q as 50, z as 2. I am getting sigma z as 5.96 kilonewton per meter square. Now if I will put r is equal to 1 meter as I am told to find out up to 3 meter. I am putting r is equal to 1 meter in the same equation with q50 and z2. I am getting sigma z as 3.41 kilonewton per meter square. Now the value has got decreased. Let us move further to r is equal to 2 meter and putting q, z and r is equal to 2 meter. I am getting sigma z as 1.05 kilonewton per meter square. You can see that it further got decreased. And the fourth item, stress at r is equal to 3 meter. And putting all the values, I am getting sigma z as 0.313 kilonewton per meter square. So the value is getting decreased. So it is as per our theoretical understanding, as we have seen the graph for vertical stress on a horizontal plane, in which if you remember that the maximum point what was at center only and then it got decreased. So the problem also shows the practical application. Let us keep our session up to this. We will meet in the next video with further problems. Thank you.